Hello everyone, this is Dr. Ian. For today, we're going to be working on the similarity between or among right triangles given its altitude. For today, we're going to be working on a different type of right triangles because this time we're going to be working with triangles with subtriangles given by the altitude of the right triangle that we're going to be working on to solve the similarities between these special types of geometric figures. So the first theorem that we're going to be working on would be the altitude of a right triangle theorem, wherein the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. So to give you a better visual of this particular theorem about right triangles, so let's say we have a right triangle that is looking like this. So we know that this is a right triangle. Forgive me for my crooked right angle, but this is a right angle and this is the opposite side of the right triangle. Let's call this triangle A, B, C, and this right triangle, let's say that we know the altitude or the height of our right triangle, which we know is perpendicular to the base or the hypotenuse of our right triangle. Therefore, we'll be able to produce two subtriangles that are considered to be similar to our main triangle. So this subtriangle ADC is similar to triangle CDB to our main triangle ABC. And when this right triangle happens, altitude of a right triangle theorem will occur. So this is basically the first theorem or the main theorem that we're going to be using that will allow us to use the corollaries that will help us in solving some of the missing parts of our triangles today. So let's say we have this right triangle and we know that this right triangle, if we rotate it, it will look similar to the triangle that we are talking about in this particular theorem. So if you're seeing triangle XYZ that is positioned this way, if I draw my right triangle similar to this triangle this way, we know that this is a right triangle and this is the line segment that is a perpendicular to our right triangle or the altitude of our right triangle, and this is triangle XYZ. The height is represented by ZW. So let's say it's ZW. Now to make it more reference to this particular triangle, so let's change the position of our 3 points and let's call this Y, X, and Z. And now we're seeing that this right triangle is similar to the first triangles that we have worked on. Therefore, we can say that this is similar because we will be able to produce three different triangles from this set of right triangles given the main triangle XYZ that shares the line segment YW, which happens to be the altitude of our main right triangle. So this is our second or first subtriangle, which is triangle ZWY. And the last subtriangle, the smaller triangle, which is YWX. And all these three triangles are similar or proportional to our main triangle XYZ from the theorem that we just had from the previous slide. So now that we know how to set up and visualize how the altitude of a right triangle theorem works, let's say we're going to have an example that uses triangles of this particular kind. But before that, let's talk about geometric mean because we're going to be working with proportions because when we talk about similarities, expect that there will be proportions that we're going to be using to help us solve our polygons for today. So according to the geometric means for any two positive numbers a and b, the geometric mean of a and b is the positive number x such that a over x is equal to x all over b. And notice that we are sharing the same variable x for this particular proportion, and we're going to use this, let's say, in this particular example when we are looking for the geometric mean of 6 and 15. And if we're going to be looking for the geometric mean, which is the first or the second diagonal of our proportion, applying this particular formula to a all over x equal to x all over b, knowing that a is equal to 6 and b is equal to 15. We are looking for the means and we are given the extremes, which is a and b. And by doing cross products or cross multiplication, we'll have 6 times 15 equal to x times x, which gives us 90 equal to x squared. And from here, we'll be able to find the value of x, which is taking the square root of both sides will give us positive or negative square root of 90 and x. But we know that since we are dealing with measurements in geometry, we're going to ignore the negative value of our x in this particular equation, and we'll just focus to the positive value of our x, which is square root of 90, which we can further simplify into 9 and 10, which gives us 3 and square root of 10 as the simplest form of our radical expression square root of 90. So in this lesson, you need to know and have mastered your multiplication table to be able to easily and conveniently find the values of x or y or z's that we're going to be working on in our lesson today. So from a over x is equal to x over b, we know that a is 6 and b is 15. We did cross products, and from here, we're able to find the values of x by taking the positive value of our x, which is positive square root of 90, which we can simplify into 3 square root of 10. And now that we know how to find the geometric means given the extremes of our proportion, let's work on the first corollary from our similar triangle theorem, wherein you are seeing that line segment CD is the height or the altitude of our right triangle. And in this first corollary, we are seeing that our height is given in this right triangle. And to be able to better visualize it, I will rotate my given right triangle into this shape or form so that I'll be able to visualize my proportion better. So in corollary 1, we know that we are given the height of our right triangle, which is given by 4 units, and we are given the segments of our hypotenuse, and we have two values of our subsegments of the hypotenuse, which is 2 and 8. 8 is the longer side or the longer measurement, and 2 is the shorter measurement of our hypotenuse. And when this happens, when the altitude is given, we can use this particular formula wherein 4 or the geometric means is given, and the extremes will be our hypotenuse segments, which is in this case 2 and 8. And this is now how we formulate our proportion based on this given right triangle that is satisfying corollary number 1. Now notice that if 2 and 8, even if you interchange it, the value will still be the same. So don't get too caught up with how the position of your values are, because in this particular form, you will still be able to get the correct proportion with this particular setup. So this is our first corollary wherein the height of our right triangle is given. Now, let's say we have this second set of similar right triangles given by line segment CD. We will call this corollary number 2 because in this particular theorem, our altitude is no longer given. And how are we going to set up our proportion in such a way that it will satisfy our corollary number 2? So let's have our diagram. So in this diagram, we have this triangle, and we know that this side is given, which is 2. We are given the measurement of this little right triangle that is formed by our line segment over here, which is our altitude for this right triangle. And we are also given the measurement of the main hypotenuse, which is equal to 4. So when this happens, that the height or this line segment is not given, we can use corollary number 2, which is giving us 2 proportion. And in this case, this will represent hypotenuse all over leg of the main right triangle equal to the hypotenuse and the leg of our sub triangle. So what is our main triangle right here? The main triangle would be the big right triangle right here. And we know that the hypotenuse of the big triangle is 4 all over the leg that is given. So we have 2 legs, but we are given the shorter leg, which is 2. So this will be our first proportion, 4 over 2. And our second proportion would be between these 2 triangles that we have. So this is our first sub right triangle, and this is our second sub right triangle. And between these 2 triangles, we'll use this because we have more information about this right triangle, wherein the measurement of our leg is equal to 1 unit and the measurement of our hypotenuse is 2. And we know that this is the hypotenuse because hypotenuse is always opposite the right angle. So now we have the second proportion of our similar triangle, which is going to be hypotenuse is 2 and leg is equal to 1. So this is now our proportion for this particular triangle, which uses corollary number 2. And in this right triangle, we know that the given altitude is not given. Therefore, when that happens, we can form our proportion as such, which is equal to 4 over 2 equal to 2 all over 1. So let's use those corollaries to solve our similar triangles, starting with this triangle wherein we are given a right triangle with the measurement of our hypotenuse and the altitude of our right triangle, which is represented by y. And what we're going to do here is to find the actual value of x and y using the corollaries that we just had. So let's work with the easier right triangle that we can work on, which is the first corollary. So if we rotate our right triangle, we know that y, which we are looking for, is the altitude of our right triangle. So given that this is our right triangle, and we know that the height of the right triangle is y, which is what we're looking for, we know that the measurement of our hypotenuse is given by line segment 4 and 12. And with this, we can form our expression, which will give us the geometric means for y, and the extremes will be our hypotenuse or the segments of our hypotenuse, which is 4 and 12. And now that we have formulated our equation, which is the most important part of our problem in solving right triangles similar to this one, we can now use algebra and perform cross product. So we will have 4 times 12 equal to y times y. And from here, we'll be able to solve for the value of y, just like what we did on our previous example. So now that we have our proportion, given that the height of our right triangle is y, and the hypotenuse is equal to 12 and 4, depending on the measurements that we're using. And again, don't worry about interchanging 4 and 12, because even if you interchange it, the value will still be the same using this proportion. And knowing that y and y is y squared and 12 times 4 is 48, now we are ready to simplify our value by taking the square root of y, which is 48. And we know that 48 is not a perfect square, but we can simplify this by taking the factors of 48 with a perfect square, which is 16 and 3. And we know that the square root of 16 is 4, so the value of y is 4 and square root of 3. And now all we need to do is to find the value of x in this right triangle. So ignoring the value of y, now we can use corollary number 2, because this time we are given one of the legs of our main right triangle. And with that, let's figure out a way on how to produce the proportion that will help us writing out the equation that we need to solve for the values of x. So first, let's visualize our right triangle. And we know that this is our right triangle and this is x. And we know that the shorter leg is 4 and this is 12. So now that we have this right triangle, we are given the hypotenuse. And the leg of the main triangle, we're going to be using hypotenuse over leg equal to hypotenuse all over leg. So for the main triangle, our hypotenuse is 4 and 12. And the leg will be the value of x. And for our second right triangle, because we know that this is right triangle 1 and right triangle 2, or we can do 2 and 3 and the main triangle is 1. But between these two right triangles, we know that we're going to be using this right triangle because we have more information. With this right triangle, we know that this is 4 units and this is x. So using this proportion, hypotenuse is equal to x and the leg is equal to 4. And by cross multiplication, we know that 4 plus 12 is 16. So now our equation will be 16 times 4 equal to x squared. And this is now the equation that will help us in finding the value of x that we are looking for. So we have our proportion and we're able to produce the correct value of our proportion for the two right triangles that we are using, the main triangle and the little right triangle right there that you are seeing right now. And by cross product, we know that 64 is a perfect square, and the value of x squared when it's equal to 64, it's either positive 8 or negative 8. But since we are working with the measurements of a triangle, we're going to use just the positive value of our x, which is equal to 8. And now we have the values of x and y, which is 4 squared of 3, and the value of x, which is equal to 8. So those are the two corollaries that we're going to be using whenever we are given a right triangle and its altitude. So with that, we're now ready to solve this problem right here given with this diagram, and we're going to find the distance between point A and point D. Now, this particular diagram, as we are seeing, is a right triangle with its altitude that cuts our two sub-triangles into two similar right triangles. So therefore, we can use corollary 1 or 2 to help us find the value of AD. And in this case, we're going to be using corollary number 2 because we know that the altitude is not given. We are given one of the legs of the right triangle, and we are given the segment of our main hypotenuse, and we're looking for the other segment of that hypotenuse using corollary number 2 because we know that our height is not given. And with that, the first thing that we need to do is to find or sketch our right triangle. So since we're using corollary number 2, we are given 20 and 9 inches, and let's say that this is 20 and this is 9 and this is the value of x. So we're going to be using the proportion hypotenuse all over leg equals hypotenuse all over leg. And the main hypotenuse is going to be this length, and it will be the sum of 9 and x. So our first hypotenuse is 9 plus x, and our main leg will be equal to 20. And now for our other proportion, we'll either use this right triangle or this right triangle, and we know that between the two of them, this one has more information because we know that the hypotenuse is equal to 20, and we know that this is the hypotenuse of this little right triangle right here because it's opposite the right angle, and our leg is equal to x. And now we're ready to write our proportion, which is hypotenuse all over leg. And now we have an equation that will help us find for the distance between A and D. So now that we have our equation, by cross product, we'll have 9 plus x multiplied to x equal to 20 multiplied to 20. And by simplifying our equation, we'll have 9x plus x squared is equal to 400. And by subtracting 400 on both sides, we are now going to produce a quadratic equation that is factorable. So our standard equation would be x squared plus 9x minus 400 equal to 0. And from here, we'll be able to use factoring. Or if you want, you can use the quadratic formula or even completing the square technique to find the solutions of our equation. And now that we're able to produce our equation based on our proportion, we'll be able to produce the solution of our equation based on this right triangle. So we know that our geometric means is going to be 20, and our extremes will be based on our right triangle numerator, or the hypotenuse of the main diagonal is x plus 9, and the hypotenuse of our little right triangle is going to be equal to x. And from here, we're able to produce our equation by using cross products and setting our equation to 0. Now, if you have mastered your multiplication table, finding the factors of 400 or negative 400 that will equal to positive 9, when you add them up, will be a lot easier. So to set up our equation, we'll have x squared plus 9x minus 400 equal to 0. Now we know that this is factorable because we're looking for the factors of negative number. So when the factor is negative, we know that their product is positive and negative. And when you add them up, it needs to equal to 9. And if you have mastered your multiplication table, this will be a little easy. But if you haven't, I'm going to show you a math hack that will help you master your multiplication table by this helper right here, which is Desmos, one of my favorite apps to use in algebra. So in Desmos, all we need to do is to write out the equation or the quadratic equation, and it will help us produce the solutions of our quadratic equation. So we have x squared plus 9x minus 400. And now we're seeing negative 25 as one of the solutions, and positive 16 as one of the solutions of the quadratic equation. And we know then when we are talking about solutions in relation to the factors of the quadratic equation, it's always the opposite values of our x. So the factors of x squared plus 9x minus 400 is simply positive 25 and negative 16. And we're able to produce that because we know that if we add negative 16 and positive 25, negative 16 plus 25 is positive 9. And when that happens, x minus 16 equal to 0 and x plus 25 equal to 0 is going to be the solution of our quadratic equation for this particular triangle. However, since we know that we're working with length of a right triangle, this is what we're going to be using, and we're no longer needing negative 25 in this solution because we're talking about lengths. And when we're talking about lengths and measurement in a word problem similar to this one, we're always going to be using its positive values. So now we have our solution, which is x is equal to 16, and the distance between that robot to the empty water bottle, or maybe a filled water bottle, is equal to 16 inches based on the similarity that we have just covered. So in this lesson, let's see if you'll be able to answer our Numberbender challenge of the day. And you're seeing a map, and that particular map is giving you a right triangle and its altitude. And what you need to do is to find the distance across that little lake that you are seeing right now. And that is our lesson for today about similarities according to this special theorems about right triangle and its altitude. And again, to be able to use this theorem, you need to know which corollary will fit your problem and make sure that you are writing your proportion correctly, because this will help you write the equation that will help you solve the variable that you are working on. This is Dr. E, and see you again next time. Bye!